Hey, welcome to The Explainer. Today, we're going to break down a really interesting paper that zooms in on a tiny, super technical detail in how we train large language models. And it turns out, this one little detail could be the difference between a stable, reliable AI and one that's just constantly getting tangled in its own leash.
All right, so let's stick with that analogy, right? The leash, because it's at the absolute heart of what we're talking about today. Imagine you're training a very smart, very powerful dog. You want it to learn all these cool new tricks, but you also got to make sure it doesn't just bolt and chase after every squirrel it sees. So how do you find that perfect balance? That's pretty much the challenge AI developers are up against every single day.
And this whole thing really gets at one of the biggest challenges in AI, the alignment problem. I mean, it's the big question, isn't it? How do we make sure that as these AI systems get more and more powerful, their goals stay aligned with ours? We need to know they're doing what we actually intend for them to do, safely and reliably.
So one of the key tools we have for this is called reinforcement learning from human feedback, or RLHF for short. You can think of this as the positive reinforcement part of the training. When the AI model nails a complex math problem or spits out some really clean code, it gets a reward. It's the good boy or the treat in our dog training analogy. It tells the AI, yes, do more of that.
But here's the thing. Just handing out treats isn't going to cut it. An AI might overfit to the reward, find some weird loophole to get the treat without actually learning the skill we want it to. And that's where something called regularization comes in. This is the leash we've been talking about. It's a mathematical penalty that keeps the new learning model from wandering too far away from its original, stable version. It keeps it grounded.
Okay, so here's where it gets really interesting. It turns out there's not just one way to, attach this leash. In the world of AI development, two main styles have popped up for doing this KL penalty. And for a long time, a lot of people kind of thought, they're pretty much the same thing. So the first way, let's call it in reward, basically bundles the pull of the leash right into the treat itself. The model gets a reward, but that reward is slightly smaller depending on how far it's straying. The reward and the penalty are all mixed into one signal. Then you've got the other way as loss, which keeps them separate. The model gets its reward, and then separately it gets a penalty from the leash.
And look, this isn't just some abstract academic thing. We're talking about the big guns here, the major widely used algorithms that actually train these models. For instance, PPO, which is a real workhorse in the field, it typically uses that in-reward style. But then you have newer methods like GRPO, which was used to train some really powerful models like DeepSeek Math, and it uses the as-loss style. So these are fundamentally different ways of holding the leash.
Okay, so which one's better? The in-reward or the as-loss? Well, for a long time, the thinking was all about how well these methods could estimate the mathematical value of the KL divergence. But the authors of this paper, they basically say, nope, you're all looking at the wrong thing.
They're saying, stop worrying about the length of the leash, how far the model has strayed, and start paying attention to the pull of the leash. And in the world of AI, that pull has a name. It's called the gradient. The gradient is simply the signal that tells the model which way to go to get better. It's the actual force that's guiding the whole learning process. And really, this is the aha moment of the whole paper. This quote nails it. It's not about just measuring something static. It's about the physics of the training process itself. To build a good leash, you have to understand the force it's applying, not just how long it is.
All right, so what happens when you do that, when you start looking at the pull of the leash instead of its length? Well, a really clear picture starts to form, and it turns out some of these commonly used methods are surprisingly broken.
So the authors kick things off with this killer counterexample. They look at a popular way of measuring the leash's length, an estimator known as K1. You might think, okay, great, it's an unbiased way to measure the distance, let's just use it as a loss. But here's the kicker. When you actually look at its gradient,
The punchline is, its expected gradient is 0. A big, fat 0. What does that mean? It means, on average, that leash isn't pulling at all. It doesn't guide the model back where it should be. It's just adding noise, basically static, into the training, which could even make things worse. An unbiased measurement created a totally useless guide.
So this new gradient-centric view, it creates this really clean split. On one side, you have what the paper calls principled methods. That's the K1 and reward method that PPO uses, and another one called K2 as loss. Their gradients work correctly. They consistently pull the model back. But on the other side, you have the K3 as loss method used in GRPO. And it turns out it's just a biased approximation. It only really works when the model is already super close to where it's supposed to be.
And this chart just makes it so obvious. The principled methods are like a perfect bungee cord. The further the dog pulls, the stronger and more consistent that pullback becomes. It's reliable. But the flawed approximation? That's like a frayed old rope. When the dog gets too far away, the rope can just go totally slack, providing no pull at all. Or in other cases, it can yank back way too hard and just destabilize everything. It's just not reliable.
Okay, so why should you care about all this? I mean, it seems pretty in the weeds, right? Well, this isn't just some academic squabble. Getting this leash right is absolutely fundamental if we want to build the next generation of powerful, reliable, and, most importantly, well-aligned AI systems.
And what's great is that the paper lays out some super clear, practical takeaways for anyone building these things. First, just don't use K1 as a loss, ever. It does nothing. Second, you should really prefer the principled methods, K1 in reward, or its proven equivalent, K2 as loss. And third, if you absolutely have to use approximations like K3 as loss, you better understand their flaws and be ready for some potential instability.
You know, in the end, this is about way more than just fixing a bug. It pushes us to ask a much bigger, maybe even uncomfortable question. If a detail this fundamental, something used in major AI models, was based on a flawed assumption, what other best practices or rules that we all take for granted are actually holding us back? It's a huge reminder that to build truly intelligent systems, we have to constantly question what we think we know and build on a foundation of sound principles.